Welcome back to my survival guide in mathematics for economists. And today we will discuss some more rules for how to differentiate different types of equations. And so far we know that if we have an equation that looks like this, f of x, a function of x, is simply a constant a, then that implies that the derivative of this function with respect to x is 0. So the slope here, if you think of this derivative as a slope, is exactly 0. It's flat like Denmark. Right, and that's quite logical because we see here that x doesn't come into the equation, and hence if we change the value of x, we really will not change the value of the function itself. So f prime of x of this equation with only a constant is 0. We have also learned the following rule, the power rule. Namely, if we have a function like this, f of x is equal to x to the power of a, that implies that the derivative of this function with respect to x is a, that is the exponent, comes down here, times x to the power of a minus 1. That we have seen so far. Still, there may be other types of functions and other types of expressions that you may have to take the derivative of. And so one of these types of functions that you can, or equations that you may come across, is sums and differences with different expressions of x. So here is one example. Let's say we have a function capital F of x, and that is composed of two different functions of x. The first one is f of x, some sort of function. We'll see an example in a moment. And then we have plus or minus, it could be either or. And then we have a function that we call g of x. So, as we have seen before, this is one function of x plus some other function of x, or minus some other function of x. Now, if it looks like this, it's quite simple. It's like two strangers on the street, they don't really affect each other. If something happens to this f of x, nothing much happens to g of x. So this implies then that the derivative of capital F of x with respect to x, of course, is then the following. It is simply f prime of x plus or minus, depending on which it was, g prime of x. Hence, the derivative of this function here is simply the sum of the derivative of the function f with respect to x and the derivative of the function g with respect to x. So that is quite simple. So let us look at one example. So let us assume that f of x is equal to 2x plus x squared. Now, this would then correspond to the x squared, could then correspond to g of x, and 2x would correspond to f of x. So, what is then the derivative of this function with respect to x when we have two functions of x added on like this? Well, let's see. So, f prime of x is equal to, so the derivative of this function with respect to x, and from before we know it's simply 2, right? Plus, and what is the derivative of this? Then we have to apply the power rule, so it's the exponent drops down here, so we'll have a 2, and then the x, and the new exponent will be 2 minus 1, that's just 1, so it's 2x. So we can see here that the derivative of this function with respect to x this one here, is 2 plus 2x. There may be other types of functions that we want to take the derivative of with respect to x, and here is another class, namely a product. And by that I mean a product of two different functions of x. So let's assume we have a function on this form. F of x is equal to, and now we bring back our old friend f of x, and this time we will multiply f of x by g of x. Now we see here that, these two are much closer, right? And they are more interdependent than in the additive case, as we saw in the last case here. Because if we do something here, it's going to be multiplied by the value of this and vice versa. So now that we have this type of equation, what is then the derivative of this function with respect to x going to be? Now, the rule for this, and you can look at the derivation for that in the Sydsaeter book, but I'll just write up the rule here. It's quite simple. It's f prime of x, that is, we take the derivative of the first function of x, times the g of x, that is, not taking the derivative of g of x, but just having the level here, plus, and then we have f of x times, then we take the derivative of g of x. Okay, so this is the rule, and so we can think of this as we will have an example in a moment, but when we change x, it's going to have two effects, right? It's going to affect the whole equation, first here and then over here. So if we think of this part here of the derivative, here we see, okay, here we see what happens to f of x when we change x a little bit. Okay, this change here will be amplified by the size of g of x, the level of g of x. So for a given size here, it's going to be bigger if this is big, right? Because we multiply something by something that's big. And vice versa, if we look at the derivative of g with respect to x, if this derivative is multiplied by f of x, if f of x is big, then this change here will have a great impact. So that is very abstract. So let's look at one very concrete economics example. Let's consider a monopolist. And we know that's the only seller in the market, right? So this is the only firm that's selling some good in some market. And that is going to have an effect on the price in the market because it's the only seller. And let's assume that x, that is the sold quantity, that is how many, how much of the good that the monopolist sells in the market. And then, of course, we have the consumers, and for them we need to define a demand function, or in this case an inverse demand function, which is basically saying that, okay, for a given level of output here that is sold, what is then the price that's going to be in the market? And the more you sell, the less people are wanting to pay for it, right? If you increase the number of goods in the market, the lower the price will be. And that is captured by the inverse demand function, this one. So P, that's the market price, is a function of X. So market price is a function of how many goods are sold in the market. And we will just assume it looks as follows, namely 10 minus 2x. So we see here if no goods are sold, the first item sold would sell for a price, if this is 0, for 10. If we're selling one good, then the price is going to be 8. 2 goods, the price is going to be 6, and so on and so on. So the higher the quantity, the lower the price, hence the inverse demand function. So a monopolist may then be interested in how much money it earns. And now we're not going to bother about any cost function, we will just look at revenue. That is how much money is coming into the monopolist. So revenue. We will define that as R as a function of X. So depending on how much of the good the firm is planning to sell, that will affect revenue, and it will affect it in two ways. We'll see that in a moment. So what is then the amount of money that the firm actually will get from selling X number of goods? Well, of course it's going to be the number of goods, right? If you're selling 2 cars, then to calculate the revenue, we must multiply the number of the cars 2 by the price it fetches in the market, which is P of X. Right. So and if we then put in the equation for the inverse demand for that is P of X, we will have the following: X, or we can even do it this way. Let's denote the X with the blue color. If I can get the blue color, X times, and then we have the inverse demand, which was 10 minus 2x. So here we have a product, right? Here's one function of X, a very simple one, X, and this is the equation for the price. So quantity times price, that is revenue. So how much should then the monopolist sell? Well, in order to calculate that, the monopolist wants to figure out what the marginal revenue is. And what is marginal revenue? Well, that is the amount of revenue extra you get from selling one more unit of whatever you are producing, a car, for example. So, marginal revenue, that is going to be the derivative of the revenue function. So how much does revenue increase or decrease when we change X by a small amount? And we can see that X comes in 2 parts here. Here it comes in positively. The more you sell, the more you should earn, right? But this is affected by also the price that it fetches in the market, and we can see from that equation that the more you sell, the lower the price. So there are 2 effects of X here. So what is then the... we can also see that if we increase the amount of goods sold when we have a high price, then there should be a rather high effect of this increase in sales. And vice versa, if the quantity of the goods sold is high, then a given price decrease or increase will have a large effect on revenues. So what is that marginal revenue? Well, I just told you that it was the derivative of the revenue function with respect to X. And here we have 2 functions of X multiplied. So it's the product rule. So it's then going to be, well, if we take the derivative of X with respect to itself, it's just going to be 1, right? Times. And then we just plug in this equation. If we go back and look here, it was f prime of x times g of x. So here we put in g of x, which is simply 10 minus 2x plus, and then according to the rule, it says here that it's f of x, taking f of x without the derivative, times g prime of x. So it's going to be x times the derivative of this red part here, which, what is that? It's minus 2, right? 10 goes away, the x goes away, it's minus 2 that's left. Times minus 2. Okay, and we can simplify this a bit. So what do we have here? Since we multiply by 1, there will only be 10 minus 2x here. Okay, and what do we have here? We have plus x times minus 2, that's minus 2x. and this is then equal to 10 minus 4x. Right, and there you have it. The marginal revenue, and you can see that the slope of this curve, incidentally, you see here it's 10 minus 4x. We will see soon that the slope is minus 4, right? For one step to the right in this diagram, we will take 4 steps down. Compare that to the demand, inverse demand, we see that, ooh, the slope is half as negative. 1 step to the right, 2 steps down. And we will come back to that in the course Intermediate Microeconomics. But here you can see how we can apply the simple product rule, for example, when we calculate marginal revenue. Now we have seen how the product rule works and apply it to an economics example. Still, there may be other functional forms that you may come across, and since you may do that, this is also very useful to know something about. E. If we look at a function with two functions of x in it, and it is a quotient, that is a function, one function of x divided by some other function of x. And more precisely, it is f of x is equal to lowercase f of x divided by g of x. Now this is a bit more tricky, and you will see that the rule is simply the following. Again, for a derivation, look in the Sydsaeter book if you don't believe me, but basically it is the following. It is just like as in the product rule, it is f prime of x times g of x, same start, right? Then we have minus, and then we have f of x times g prime of x. But no, it doesn't end there. There is yet another item here, namely the denominator, which is then the following. It is g of x to the power of 2. So this is a bit tricky, right? So you must remember that the f prime times g of x, that comes before the negative sign here, right? It's a negative sign, so it matters on which part, if you put the f prime here or over here. So make sure you remember how to do that. So let me show you one quick example. So assume that f of x is equal to 2x divided by x squared. So up here we have f of x, and down here we have g of x. So then if we apply our rule, then we see here, okay, first we have the f prime of x, that's f prime of that, that's only a 2, right? Let's make that, so this is the blue part, this is the red part. So the first thing here, f prime of x, that's just a 2, times g of x, which is x squared, minus, and then you have f of x, which is 2x, times g prime of x, and the derivative of this with respect to x is simply 2x divided by, and then in the denominator we have g of x to the power of 2. So it's x squared to the power of 2. And we can simplify this as the following. Here we have 2x2 minus 4x2. Divided by x to the power of 4, right? X squared to the power of 2, that's 2 by 2 is 4. And we can simplify this a bit. So here we have 2x squares minus 4x squares. So then we end up with minus 2x x squared divided by x to the power of 4. And we can, as we see here, we have x to the power of 2. X is the same base as x here, so we can simply take away this exponent here, deduct 4. X to the power of 2 minus 4 is x to the power of minus 2, and that is the same thing as writing minus 2 is the denominator, and in the denominator we have x squared. So this is the derivative of a function that was a quotient of two functions of x, 2x divided by x squared. Now, there is an alternative to this. If you don't like this rule here, this one here is kind of big and messy, right? So sometimes it is possible to perhaps make a simplification first. Alternative. And f of x was equal to 2x divided by x squared. And we can see that here is x times x and here is x. So this x cancels one of those x's, so we can rewrite this as 2 divided by x. So this will be much easier, and we can also write it as the following is 2 times x to the power of minus 1, if you remember the powers rules since before. So that implies that f prime of x, so this is a constant, so it remains, and then we apply the power rule, so x to the power of minus 1, right? So the minus 1 pops down, so there's a minus sign here. Minus 1 times 2 is minus 2. And then x to the power of minus 1 equal to minus 2 to the times x to the power of minus 2. And that is the same thing as saying that this is equal to minus 2 divided by x squared. And we are lucky here because we can see that the answer to this is minus 2 divided by x squared. And comparing it to when we apply the quotient rule, it is exactly the same. So two lessons here. One, you should learn the quotient rule, because sometimes you can't do these simplifications. So you must learn this. Two, if you can, try to simplify an equation as much as you can before you take the derivative, because you may save you some time and make it a bit easier. So in this case here, I could simplify the equation and then I didn't have to use the quotient rule, it was enough to use the power rule. So that is my suggestion to you. Finally, there is yet another class that we want to look at, namely if we have a composite function, and then we need to apply the chain rule, and this is what that is. So f, we call this the chain rule of a composite function. So this is a composite function, so two functions. Let's assume we have a function f of x is a function of f. So this is one function, and that in turn is a function of another function, g of x. So we can see there are two functions here, f, which is a function of g, and g is a function of x. So then this implies that the derivative of this composite function with respect to x is the following. It is going to be simply the outer times the inner derivative, because if something happens here, here's something happens and this increases, then that will affect this function. What happens to this when g increases? Well, it's simply the following. It is the derivative of the outer function f prime, which is a function of g of x then times the inner derivative, that is the derivative of the function g with respect to x. And so this is the outer times the inner derivative. So let me show you one simple example of this. Assume we have a function on this form, f of x is equal to something to the power of 3. So this is the outer function, right? And what's in here? Well, there's another function, namely 2x squared minus 3. So this is the inner, and the blue here is the outer function. So f of g of x is equal to this. That is simply the g, the value of g evaluated as x to the power of 3. And then the inner function g of x is 2x squared minus 3. Okay, so now we want to calculate the derivative of this whole function here. So the derivative of the function capital F of x is the following. So first we take the outer derivative, and what is that? Well, that is going to be, I'll write that in blue completely, that is going to be 3 times this to the power of 2. 3 times 2x squared minus 3 to the power of 2. That is the outer derivative. And what is then the inner derivative? Looking at this function here, 2x squared minus 3. Well, the derivative of this will be 2 times 2 is 4 times x to the power of 1. So it's simply 4x. So this is g prime of x, and this is f prime of g of x. And we can probably simplify this a bit more. So we have 3 times 2x squared minus 3 power of 2 times 4x. That is, so 4 times 3 is 12, and x. So it's 12x times 2x squared minus 3, and this is to the power of 2. So there you have it. That is the derivative of this composite function. And remember that it is the outer derivative times the inner derivative. And here is the answer. So study up on that, and I will see you next time.